Welcome to online training session, day 9, part 1, where I am going to discuss about shape optimization. We'll see about the training series details. In this, I have covered day 1 FEM theory, day 2 1D meshing, in day 3 I have covered 2D meshing, day 4 I have covered 3D meshing. In day 5, I have already discussed about the analysis and post-processing, in which I have divided the day 5 into 3 different parts. In day 6, I have covered topology optimization, where I have discussed topology optimization parameters, and I have divided that into 2 parts, part 1 and part 2. Day 7, topography and composite optimization. Day 8, size optimization, in which I have divided it into 2 parts, part 1 and part 2. Now we are on the last day of the training series, in which I am going to discuss shape optimization. This process also I have divided into 2 parts, part 1 and part 2. So in today's part, or in this part, I am going to discuss about the 2D shape optimization of cantilever beam, cantilever L beam shape optimization of 3D bracket model using the free shape method, buckling optimization of structural rail, and shape optimization of rail joint. So I will start with the first tutorial, where I am going to discuss about the 2D shape optimization of cantilever beam. In this tutorial, a shape optimization on a cantilever beam modeled with a shell elements will be performed. The structural model with loads and constraints applied is shown in figure, as you can see below. The deflection at the lower right corner should be limited to 3 mm. The optimal design would use as little material as possible. The structural model shown below is loaded into hypermesh and is used to generate and run a shape optimization of a cantilever beam. Shape permutations vectors are generated using hypermorph, which is a tool in HyperWorks suites, then which is accessed through hypermesh interface. The OptiStruct software is used to determine the optimal shape. The results are then reviewed in Hyperview. So the optimization problem for this tutorial is stated as: my objective is to minimize the volume. My constraints are given maximum nodal displacement at the end of the beam should be less than 3 mm. My design variables are shape variables defined with hypermorph. So I will give different shapes using hypermorph, and with this, say 2 or 3 shapes, I will ask OptiStruct to get me a preferred shape or the best shape for my constraints. So in this tutorial, we will see how to set up the shape optimization problem in hypermesh, post-process the results in Hyperview. So I will open the hypermesh 12 window. Select the user profile as OptiStruct, because we are going to perform the optimization. So OptiStruct is a solver for optimization. So this loads the user profile. It indicates the appropriate templates, macro menus, and import readers, paring down the functionalities of hypermesh to what is relevant for generating in world data format for Radius and OptiStruct. So if you are not able to see the user profile window, you can click on this user profile window, this icon where you can load the user profile. Now open the folder and browse the file. So this is the file on which I am going to, this is the beam on which I am going to perform the shape optimization. The material, properties, component, load collectors, and load step is predefined. So the base analysis things are already defined. So we will directly start up by for the shape optimization to setting up the problem for shape optimization. So I will minimize this. So my first step is to create the shape using hypermorph. So for this, I'll go to analysis page optimization panel, which you can see here. In this, I will click on hypermorph. So this is the hypermorph panel, which is on second column, last row. Click on domains. First, I will create the domains. Then I will click on global domains to auto functions and click on generate. So once you click on generate, a number of domains and handles are created. The reds are domains, the yellow ones, as you can see if I zoom it here, the yellow dots are the handles, as you can see here. So a number of domains and handles are created which will enable us to morph the shape of the beam. There are two types of handles, global handles which are represented by large red balls, local handles which are represented by small yellow balls. Only the local handles will be covered in this tutorial. So we'll change the shape with the help of local handles, that is the yellow shapes which you can see here. Then we'll click on return. Then we will click on morph to enter the morph panel. Then select move handle radio button. Then click on handle. And select this handle. From this option, it's interactive, move it to move to node. So click on the handle, select the node, so it will get moved, as you can see. So this is my first shape change. So I will save this shape. So click on save and save as first. Change the color. Make sure the option is set to as node perturbations. Click on save and it will ask us that save perturbation for nodes for at a global and morph volume handles. Yes. So save this shape and click on undo all. So my original beam shape will get attained and it will create a shape using this 4 arrows. Then click return. Then click on handles panel to create one more handle. Name it as aux1. Say I'll name it as aux1. Click on domain and select the top edge for the domain. Select by node and select the top or the center node of this and click create. So a new local handle will get created here. So with the help of this I will create one more shape. So click return. So click return to go back to the hypermorph menu. Then again click on morph, keep move handle, select this node, move to the center node. So this is my next shape. You can also do the biasing. As you can see, the meshing is not appropriate. So there is a dense mesh, here is not. So we can also change the meshing. So click on set bias and off this red ball so that you can see this handle. So select, click on this handle So you can see biasing factor is, you can see here. You can increase the biasing factor by left clicking on that number and click on update. So once you click on update, you can see it did a biasing. So the meshing is little good. So you can also change this. So this, in this way you can set the biasing, and we will save this shape again. So I will name it as shape 2, change the color again as node permutations. Click on save, yes, and click on undo all. So I have two shapes, shape number 1 and shape number 2, as you can see here on the model browser. So click return to go back to the hypermorph menu. Again click return to go back to the optimization panel. Now we will define the shape variables which I have defined. So click on shapes. From this single DSVAR, that is design variable, change it to multiple design variable. Click on shapes, select both the shapes and click on create. Keeping all the parameters as it is, click on create. So my design variable is created. Then click return to go back to the optimization panel. Now the next step is to define the responses. So I will have two responses, one for objective, one for constraint. So I will first create the first response as volume. Select the response type as volume. Keeping all the parameters as it is, click create. So my optimization response has been defined. Then I will create one more response as displacement. Select the response type as static displacement. Select the node on which I want the displacement to get lower down. So I will select this node, or you can enter it by ID as 1115. So it will get selected. Select the degree of freedom 1 because it's an x-axis. So the force is acting on x-axis. So the translation will act on x-axis. So I want the constraint to be on x-axis. You can select total displacement also. It will not affect the results more. Then click create. So my second response is also defined. Now I will create the constraints and objective. So click on D-constraints to define the constraints. Enter the constraint name as, say, constraint. Select the response as displacement, load step as load. Check the upper bound and enter the value as 3. Click create. So my constraint is defined now. Now I will define the objective. So I will click return to go back to optimization panel. Then I will click on objective. My objective is to minimize the volume and click create. So my constraint and objective is defined. Now we will define a shape card. So only the displacement and stress results are available in the SH file by default. In order to look at the displacement stress on top of the shape change that was applied on the model in hyperview, a shape card needs to be defined. So if you want to see the displacement value by seeing the shape change both at a one file, you have to define a control card. So click return, go to analysis page. On analysis page, click on control card. Click next. Click on shape. Select the type as all and option as all. Click return. So with this in hyperview, once the result we will get in hyperview, we can see the shape, changed shape of the model as well as the displacement value at one point. Okay, so click return again to go back to the main menu. Now I will save this file and solve it using OptiStruct. So I'll go to File, Save As. In desktop I will create one more folder as tutorial 1 and save. Then I will go to Analysis, OptiStruct, select the export option to all, run option to optimization. Memory option I will keep either as default or enter the upper limit in MB as 1000 and click on OptiStruct. So once I will click on OptiStruct, it will start the solver window, as you can see. So it will start performing iterations. So when optimization has converged and feasible design has achieved, I will click on results to view the results in Hyperview. So I will have the fifth. So this is the shape. Apply. So this is the shape change. And if we click next, so this is the shape change and the displacement values. So you can see the displacement is not exceeding 3. It is 3.01, which is nearly the 3.1. So while changing the shape, we have achieved the desired constraints. So in this way, we can perform the shape optimization by providing the different shapes, appropriate constraints, and performing the analysis. So with this, I have ended the first tutorial. So I will close the Hyperview. Click on New. Now we will move to the next tutorial, that is Cantilever L-beam shape optimization. So this tutorial focus on performing a shape optimization on L section cantilever beam model with a shell element. A systematic is shown in a schematic is shown in figure below. The vertical deflection at a point N, as you can see at the bottom, should be limited to 2 mm while minimizing the amount of material required. The optimization problem for this tutorial is stated as: my objective is to minimize the mass. My constraint is given maximum nodal displacement should be less than 2 mm. My design variable is the shape of each element of the beam flange. In this tutorial, we will see how to set up the shape optimization problem in HyperMesh. Post-process the optimization results in Hyperview. So let's open the HyperMesh. Make sure the user profile is set to OptiStruct. Open the file. So this is my model with constraint at one end and force is applied on the other end. So on the model browser, you can see my material, the properties, materials, component, load collector, load step is predefined. So I will directly start with setting up the shape optimization problem with the help of HyperMesh. So my first step for this is to create shapes using Hypermorph as we did earlier. So I'll go to Analysis, Optimization, Hypermorph. Then click on Domains. And click Generate. So this will generate local and global handles. You can see here. So the yellow dots are the local handles and the red balls are the global handles. So click Return. These handles, with the help of these handles, we can create the different shapes. Now click on Morph. select move handle. Now we will select translate instead of move to node. Now select the local handle, this. Enter the Y value as -10 and click on morph. So this is the first shape change. I am showing the different options how to use it. You can use the move handle node also. So different panels are there, but I'm just showing you how to use different panels. So that's why I've used the translate command. So you can translate it to y-axis at a distance of -10. Go to save shape, enter the shape number as 1, change the color, select as node perturbations and click on save. Yes, so my first shape is saved. Make sure you click on undo all so that your model will go back to the original shape. Now I will create some more shapes. So we'll select this one, enter the value as 0. Now we will move this to -x as -10. Click on morph. Save the shape as 2. Change the color. Save. Yes. Undo all. Then this one. We'll select this. With this same morph, save the shape as 3, define a different color, save, yes, undo all. Then this handle, I will keep it as 0 and y as -10. Morph, save the shape as shape number 4. So you can create different shapes as per your requirement. Save, yes, undo all. So these are the different shapes which I have created for which I will take in the optimization, shape optimization process. So these are the different shapes which I have given to the software, and out of those shapes, it will give me the best possible shape for as required for my constraint and objective. So I will click return. Again, I will click return to go back to the optimization panel. So now I will create a design variable for shape optimization. So I will go to shape panel. So make sure the multiple design variable option is selected. Instead of single, select multiple design variable. Select the shape and select all the 4 shapes. 1, 2, 3, 4. Click select and click create. So it has created all these design variables. Now we will click return. Now we will create the next step is to create the responses for mass and static displacement. So I will go to response panel, enter the response name as mass, select the response type as mass, keeping all the parameters as it is. We'll click on create. I will create one more response as displacement. Enter the value, select the response type as static displacement. We'll select this node. We'll see whether the node is selected or not. So I will hide this and select the node. I will deselect all. Select this node and select the degree of freedom 2. Because the force acting is in y-axis, so that I want to restrict the displacement in y-axis. Now I will click create and return. So I can also click on show. So my two responses has been defined, as you can see. Now I will apply them at constraints and objective. So I will define the objective. My objective is to minimize the mass and click create. So I have defined the objective. And my response is, my constraint is to, so I will enter the constraint name as constraint upper bound to 2, response as displacement, load step, which is predefined as load, and say create. So I have defined the constraint. Now I will save this shape. Also you can activate the shape data, shape, this to all, options to all. So with this it will give us the option to view the results with the shape change for the displacement values. So I will save this file now. As tutorial 1-2. Now I will use OptiStruct to solve this model. So analysis, OptiStruct, export option to all, run option to optimization, memory option. I will enter this value as 1000 MB. Click on OptiStruct. Once you click on OptiStruct, it will start the solver. So as you can see, my optimization has converged and feasible design with all constraints satisfied has been, you can see the message has appeared. So click on results to view the results in hyperview. Click close, this is the message log. So click close. Go to the last iteration and click on shape change. So if I click on animation, I will lower it down. So you can see I will make it as a wireframe. So originally the shape is somewhat like this. Now it has changed the shape to this. So this is the new shape where it is decreasing this length as well as changing this side. Now I will see the results. I will pause it to the last iteration. Apply. Static min max. So I will add it. Select this node. if I want to see this portion, what is the displacement in this? So you can see the value of displacement with the shape change. So this is the shape change from the original. So this is the original shape and this is the change in the shape. So in this way, I have ended with this tutorial. I will close this, click new. Now we will move to the next tutorial. That is, in this I am going to discuss about the shape optimization of a 3D bracket model using the free shape method. So in this exercise, shape optimization on a solid bracket model will be performed using the free shape optimization method. The objective of this optimization is to reduce the stress by changing the geometry of the bracket model. The essential idea of free shape optimization and where it differs from other shape optimization technique is that the allowable movement of the outer boundary is automatically determined, thus relieving users of the burden of defining shape perturbations. The optimization problem for this tutorial is stated as: my objective is to minimize maximum von Mises stresses. There is no constraints in this model and my design variables are grids move normal to the surface. So in this tutorial we will see how to set up a free shape optimization, post-process the free shape optimization results, set up a new free shape optimization simulation with moving constraints, and post-process the new free shape optimization results. So let's open it in HyperMesh. Select the user profile as OptiStruct. Make sure you have selected the user profile as OptiStruct. Browse the file. So this is my 3D bracket in which I have done the 3D meshing. My material properties, everything is predefined. So let's directly move to set up a free size optimization. So first step is to create a free shape design variable. So we'll go to analysis page and analysis page I will click on optimization. In optimization, click on free shape panel, which is in first column, fourth row. Enter the design variable name, let's say shape. Select the nodes as shown in the figure. As you can see here, select these nodes. This is the area where I want to change the shape using the free shape panel. And click create. So a design variable with this node has been created. Now we will define the optimization problem. So we'll start with defining the responses. So I'll click return. Then I will click on responses. Enter the response name as stress. Select the response type as static stress. Click on the properties and select stress spaces properties. Select von Mises stress and both surfaces options. Make sure this option is selected. From the drop box you can select von Mises for the both surfaces. Click create. Then click return to go back to the optimization panel. Now we will define objective reference. So enter the objective reference name as maximum stress. Select the positive reference and enter the value as 1 as the default. Select the response as stress. Click create and return. So it will take the maximum von Mises stress. Then define the objective. My objective is to minimize the maximum von Mises stress. So select mean max and give the objective reference. That is DOBJREFS is objective reference. And click create. So my objective is defined, in which my objective is to minimize the maximum stresses. Click return to go back to the optimization panel. Now we will define the shape card. So go to analysis, control cards, shapes, type all, options all. Again click return. So now we'll save this file as run1, save. Then we'll go to analysis, OptiStruct, keeping all the parameters as it is, like export option to all, run option to optimization, memory option either default or upper limit in MB as 1000, and click on OptiStruct to start the solver. So it will start the solver window, as you can see. So now you can see my optimization has converged and feasible design has been achieved. So I'll click on results to view the results in Hyperview. So we'll select this part. Shape change, contour, wireframe, mesh. So you can see that the thickness, if I lower down the speed, the thickness of the model is increasing. You can see here. So it is increasing from the actual thickness. So it is changing the shape as free shape optimization. You can see it's changing the shape, but it is also increasing the thickness here. This is increasing this thickness also. So let's suppose due to manufacturability, I am not allowed to change this thickness, and still I want to perform a shape optimization by changing this shape, this curvature. I am allowed to change this curvature as I want, but I am not allowed to change this thickness. So now we will see how to apply the thickness constraint on the model. So I will close this. Also we will see the stress values. So I will go to next. Contour, elemental stress, simple and apply. Static mean max. So the stress value for the 0th iteration is this. and for the last iteration, that is after changing the shape, is 572. So it has changed it has minimized the maximum stress by changing the shape. So I will close this, and now we will apply a constraint so that we don't allow this to change the thickness, this thickness of the component. It can change the shape of the curved portion, but it will not change this thickness. So we'll see how to do that. So click return to go back to the main menu. Click on 1D page. On 1D page, click on systems. Then create by axis subpanel. Select it. Create by axis direction. Click on the nodes, enter by ID and enter the value as 20999. Click on origin, enter the ID same as 20999. X-axis, enter the ID as 15989. XY plane, enter the ID as 19462 and click create. So I have created a local coordinate system. So the constraint on the curved part will be created using local rectangular coordinate system. The other constraints on the flat part do not need a local coordinate system. Therefore, a local rectangular coordinate system will point normal to D-shaped surface need to be created first. So we have created this for the curved portion, a local coordinate system. Then click return. Click on analysis optimization and click on free shape. Then click on grid con. Select the design variable as shape, which we have already created. Select the constraint type as planar. And select these nodes. Click on the vector definition and select vectors. And select N1, N2 and N3 as these three nodes. And click on add. So these nodes will move only to specified plane. Now the next constraint on the curved part will be created using the local coordinate system. So select the constraint type as vector. Click on the nodes and select the nodes on the curved area. And in direction selector, select local system and click on the local system which we have created earlier. Select the direction to Z axis and click add. So now it will move to the Z direction, the local Z direction. So this is XY, so it can move in this direction only. It will not move in X or Y direction. Click return. Again click return. So now we will save this file again as run2, save, analysis, OptiStruct, and click on OptiStruct to start the solver. So it will start the solver process. So now as you can see, my analysis has converged and all feasible design has achieved. So I will click on results to view the results in Hyperview. I will move to the last iteration, shape change, and click play. So now you can see it is changing the shape, but it is not changing the thickness. You can see that it is keeping the thickness as it is. So if I click on wireframe user and say, let's say black, so you can see it is not changing the thickness, it is just changing the shape. So in this way you can provide the constraints on the thickness values. So you can see here it is not changing the thickness, it is just changing the shape. So this is the shape required. Also we can see the results of stresses with this. So static min max. So initially is 591 for the last iteration. It has increased a little. So in this way you can perform the shape optimization using free shape panel. So you haven't provided any shape to the computer or the solver. It has generated the shape as per the constraints. So in this way I have ended with this tutorial. So I will close this. Click on new in Hypermesh. Now we will move to the next tutorial, that is buckling optimization of a structural rail. So structures are to be buckled, are set to buckle when a certain combination of loads causes them to be unstable and deflection occurs. When a particular loading is reached, the structure continues to deflect without an increase in the magnitude of the load. The critical load at which buckling occurs is the product of critical buckling factor and the applied reference load. The buckling factor is an eigenvalue and has no dimensions. Generally speaking, the lowest buckling load is usually of the most interest of engineers, since a structure will fail prior to reaching any higher buckling loads. When using OptiStruct to solve a linear buckling problem, apply a reference load to the structure and calculate the buckling factor based on linear static and normal mode analysis. Use OptiStruct also to perform size or shape optimization on structure to optimize the linear buckling. Neither yielding of the structure nor change of force can occur during the optimization process. In this tutorial, a size and shape optimization are performed on structural rail to increase the buckling factor, thereby increasing the load it can carry before buckling. The rail has external force applied at one end and is constrained in all degrees of freedom at the other end. By performing buckling optimization, we can increase the buckling factor and thereby increasing critical buckling force. We want to perform buckling optimization to minimize the maximum von Mises stress among several elements. We do this using minimize maximum problem setup. use min max or max min statement to define the objective function of minimize maximum or maximize minimum problem. Many times you will need to minimize or maximize several responses. Minimizing the maximum on-matches stress among several elements. For example, in such situation, using user-defined equation to minimize the maximum on-matches stresses will not achieve the expected result. Reducing the maximum stresses in one element often results in increased stress on the other element. This tutorial describes the steps involved in defining linear buckling and size optimization using the gauge panel. Shape and size optimization will both be applied to the structure, to this structural optimization. The shape optimization has been predefined in this model using hypermorph. So you will not need to set up the shape and shape design variables. The size optimization is a part of this exercise. A reference value is given to the stress design objective and the problem is formulated as min max optimization problem. The resulting structure is thicker and wider to prevent buckling. My problem statement is this problem will perform a size and shape optimization of structural rail to prevent buckling in the rail structure. My objective is to minimize the maximum on-matches stress. My constraint is increase first buckling factor above 30. Regional volume of the designable region is less than 8 lakhs. My element design variables are element thickness and shape permutations. In this tutorial, we will see set up the buckling optimization simulation and post-process the results in Hyperview. So we'll start up by launching the hypermesh, selecting the user profile as OptiStruct, click open folder, browse the file. So this is the file, this is the rail model, that is the rail structure on which I am going to prevent the buckling. So most of the things are predefined, like the shape optimization is already predefined. Using hypermorph in this model, you can see the shapes, different shapes. If I off this meshing, so these are the different shapes you will see. So hypermorph, morph, or you can go to utility menu, Opti, select the summary as Opti, click on design variable. So you can see this is the info of the two different shapes, that is V1 and V2, which is predefined. So the initial value is 0, my lower bound is -2 and upper bound is 2. Click close, go to model browser again, on this. So everything is predefined. Now I'll go to analysis, optimization, click on shape. So now click on animate. Select simulate shape 1. Data type as permutation vectors. Click on linear. So this is the first shape change. You can see here. Similarly, you can see the second. So these are the two shape changes which I have predefined using hypermorph. Now click return. Again click return to go back to the main menu. So these are the two different shapes which I have defined using the hypermorph panel. Now we will define the size optimization design variable. So we will click return. Now we will click on gauge. Select the create radio button. Enter the design variable name as shells. Click on the properties and select shell elements and dome, both the properties. Select the type as specialty and select the same design variable for all properties. At initial bond, enter the value as 6, initial value. At lower bound, enter the value as 3. In upper bound, enter the value as 9. Keep all the parameters as it is and click on create. So one more design variable is created. Now we will create a eigenvalue buckling load collector. I will click return. Click on load collector icon. Enter the load collector name as buckling. Enter the card image as EIGRL. Click on create edit. Enter the V1 value as 0.01, V2 as 100 and ND as 20. Then click return. Again click return. So a new load collector is defined as buckling. Now we will set up a buckling optimization load step. So I will go to analysis, load step, enter the name as buckling, change the type to linear buckling, select static subchase and select linear, and in method structure I will select buckling. Click create and click return. So a load step buckling has been defined. Now we will define the responses for optimization. So I will go to analysis, optimization, responses. First I will create a response as buckle. Select the response type as buckling. Number of modes to be 1 and say create. Now the next as 1, select the type of response as static stress. Properties of dome. Select the type as one mysis and option as both surfaces. Click create. So one more response has been created. Now we will create one more response as volume. Select the response type as volume. Keep all the other parameters as it is, but changing the options to by entity and selecting the properties of dome, because I want to change the volume of the dome only. Click create and return. So I have defined three responses, one for buckle, one for static stresses and one for volume. Now we will define the constraints. I'll go to day constraint panel, enter the name of the constraint as say buckle, select the response type and select buckle, select the load step buckling, check the box in front of lower bound and enter the value as 30. It should not go below 30. The buckling should not go below 30. Click create. Then enter the constraint name as volume. Select the response as volume. Check the upper bound and enter the value as 8 lakhs. And click create. So I have defined two constraints. Now I will define the objective reference. So I will click on objective reference. Enter the objective reference name as maximum stress. Response will be 1 mises. Positive reference. Check the box in front of positive reference. Toggle all to load step and select the linear one and click on create. Then we will define the objective. My objective is to minimize the maximum stress. So click create. So in this way I have defined the shape as well as size optimization problem. Now I will save this file. Save and solve it using OptiStruct. So analysis, OptiStruct, export option to all, run option to analysis, memory option to default, or you can enter whatever memory you want and click on OptiStruct to start the solver. So as you can see, it has started the solver and the optimization has converged and feasible design has achieved. So I will click on results to view the results in hyperview. So select the last iteration with the shape change, as you can see. Also the elemental thickness, it has changed. So it has changed both the things. Elemental thickness, earlier it was this to this, and the shape change. So this is the shape change. So earlier the thickness is 6. In the last iteration the thickness has been changed to 5.7. So it has changed the thickness, it has reduced the thickness, as well as it has changed the shape of the component. So earlier it was like this, and now it has changed the shape. You can see. You can also see the animation. You can see here. So from baseline it is increasing the thickness. Now we will see the results of von Mises stresses. For 0th iteration it is 11, and for the shape change iteration, the final design, it is 10. So it has reduced the maximum von Mises stresses. Then we will see the results for buckling. So for the first, it is on the 0th iteration it is 27, but now it has increased to 33. So my buckling factor has increased, which I want, to more than 30. So it has increased more than 30. It's 33 now. Earlier it was 27, as you can see here. So in this way I have ended with this tutorial. So I will close this, click new, and we'll move to the next tutorial, that is shape optimization of rail joint. So in shape optimization requires you to have knowledge of the kind of shape you would like to change in the structure. This may include finding the optimum shape to reduce the stress concentration, to changing the cross section to meet specific design requirements. Therefore, you need to define the shape modifications and the nodal movement to reflect the shape changes. Shape optimization requires the use of two cards, that is DSVAR, that is design variable, and DV grid, that is design variable grid. They can be defined using hypermorph. Then these cards are included in the OptiStruct input file along with the objective function and constraints to run the shape optimization. In this exercise, you will perform a shape optimization on rail joint. The rail joint is made up of shell elements and has one load case. The shape of the joint is modified to satisfy the stress constraints while minimizing mass. My problem statement is, my objective is to minimize the mass. My constraint is maximum von Mises stress of the joint should be less than 200 MPa. My design variable is the shape variable. In this tutorial, we will perform an analysis of the initial design, post-process the initial design results in Hyperview, set up the shape optimization problem in Hypermesh, post-process the optimization results in Hyperview. So let's launch the Hypermesh GUI. Make sure the user profile is set to OptiStruct. Browse the file. This is the rail joint. We'll save this file. Perform a base run analysis. Analysis OptiStruct, run option to analysis, and click on OptiStruct. Keeping all the parameters as it is, we'll just perform the optimization. So my analysis has been completed. So we will see the value of maximum stress. So contour, elemental stress, maximum, simple, and apply. We'll see it. The maximum stress is coming as 242. We'll take a note of it. So the maximum stress is coming as 242.609. Now this is my objective. This is my constraint, that maximum von Mises stress should go below 200. So currently it is 242. So I will close this and we'll start defining the different parameters required to perform the shape optimization. So we'll start with displaying the node numbers. So I'll click return, go to tools, on tools, click on numbers, click on the nodes, select by set, select the node set and click on. So there are total 16 nodes that has been selected with the node numbers. You can see. So with the help of this, we will create some different shapes. Now the next step is build 2D domain on the rail. So I will right click on P shell and click on isolate. Then I'll go to analysis page, optimization, and in the optimization panel click on hypermorph. Then I will click on domains. Select the partitioning radio button. Select the domain angle to be 50 degree. Curve tolerance as 8. Then move back the radio button to create. Select 2D domain. Select all elements to elements. Elements by set. And select these two, rail set 1 and rail set 2. And click on create. So I have created the domain for these two sets, as you can see. I will off the forces also, so I will hide them. Then we'll split the circular edge domain around the opening of the rail. So I will click return. So I'll click on edit edge. Select the option as split. We will select the domain, this one. And select the node number 1311 and click on split. So this will split this curvature, as you can see. Now we will select the other domain. Or this one. Select this node and say split. Similarly, this domain, this one node, split. This domain, this node, and split. So I have defined these domains. Similarly, I will create or define the domains here also. So split, then this node, split, this domain on this domain to this node, split on this domain with this node, split. So I have splitted all the domains, as you can see here. Then we'll merge the edge domains. So each circular domain on the rail has been split at 4 nodes and 4 new handles have been added to the each circular domain. This operation results in 5 curved edge domains on each circular edge on the rail. The objective is to have only 4. Now we will merge 1. So we only will have 4, that is 1, 2 and 3 and 4. So we will merge these. These 2 domains we will merge. So toggle the option to merge. Select these 2 domains and say merge. Similarly, select these 2 domains and click on merge. So now I have 4 domains. Now we will build a 2D domain on tube. So I will click on pshell.1. So this is the tube. Toggle back to the create radio button. Elements by set. Select the first element set and click create. So the first domain is created. Similarly, element by set second, create. Elements by set third, create. Elements by set 4, create. So we have created so many domains so that I have the maximum flexibility to change the shape as per my requirement. So now click return to go back to the hypermorph menu. Now we will create the shapes. I have defined the domains. Now the next step is to create the shapes as per my requirement. So these are the domains which I have created. Now we will create the shapes. So click on morph to define the shapes. Click on alter dimensions. Select curvature. Select the center calculation and select by edge. Select the option as hold ends. Holding 2 ends of the selected edge domains allow a change of curvature of the selected edge without altering its endpoint. Leave the other settings as default. Use these domains select these domains. I think I have to merge them also. So I will click return, go to domains, edit. First I will merge these. Merge, return, morph. So I have selected all these. I will make it in the line mode so you can see. These are the white selections. Enter the curve ratio as 20 and click on morph. Then toggle it to save shape as shape number 1. Define a color and toggle it to as handle perturbations to node perturbations. Click on save. Then click on undo all and hide this shape. So this is the first shape which is created. Then again go to alter dimensions. Now this time select these domains. And click on morph. Save shape number 2. Color say green. Save. Undo all. So this is the another shape. Again hide this one too. Select apply shape radio button. Select both shape 1 and shape 2. And click apply. So this is the third shape. Save it as shape number 3. Save. Undo all. Hide this shape. Hide this one. Then alter dimensions. Click on deselect options. Toggle it to distance. So we will apply this shape and we will change the dimensions of this shape. So at end A, we will click on this. Select node to handles. I will hide these handles. Select this node and this node. Once these two nodes is selected, the distance between the nodes, you can see it has been automatically calculated. Now click on show handles and click on this 8 handles. Select these. And for node B, handles, select these. Select hold middle. Enter the distance 20 and click on morph. So this will morph the next shape, as you can see. Click on save shape, enter it as shape number 4. And click on save. Click undo all to restore the base design. And hide the shape. So in this way I have defined 4 different shapes using hypermorph. So I'll click return. Again click return to go back to the optimization panel. Now I will define the shape design variables and review the animation. So I will go to analysis, optimization and click on shapes. So make sure the design variable DES, VAR or radio button is selected. Switch the option to multiple design variable. Select all the 4 design variables. Keeping all the parameters as it is, click create. So this creates 4 design variables with the same initial value, lower bound and upper bound. So the hypermesh automatically links the design variable of each shape respectively and assign name to each design variable, the same name associated with the shape. Now click on animate. First shape and click model. So this is the first shape. Animation. This way it will move. Second animation. Third. Fourth. So these are the 4 different shapes. Now the next step is to create the responses which we'll use in optimize objective and constraints. So I'll click on responses Enter the response name as mass. Select the response type as mass. Select the option total and click create. So my response has been defined. Now I will create the one more response as stress. Select the response type as static stress. Select the property as pshell.1. Select the one voices and both the surface and click on create. So my second response has been created. Now I will create the objective. So my objective is to minimize the maximum mass, minimize the mass, not the maximum mass, minimize the mass. So I have defined the objective and my constraint is the stresses for this load step should be lower than 200. Create. So earlier it is coming as 242, but I want with the shape change the stress should be less than 200. Now we will define the control guard required for the shape optimization. So I will go to analysis control cards. Go to param. Scroll it down to check L. That is check element. No. Click return. Click return. Now I will save this file. This card will help us to skip the element quality check. Optimization. Save. Analysis of the struct. So it has started the, I have to select the run option as optimization and then click on OptiStruct. So it has started the optimization process as you can see. So my optimization has converged and feasible design has been achieved. So I will click on results to view the results in Hyperview. So first we will see the shape change. So this is the final shape change for the required parameters what I want. So you can see if I minimize the speed, go to deform, say wireframe or edges, or you can say wireframe. I can again lower it down the speed a bit. So you can see initially the initial design is something like this, but after optimization it is asking to generate a design like this to get a desired constraint, to satisfy the desired constraint. So keeping all the other parameters as it has changed the shape a little bit like this. So if I change the color, so this is the actual shape, the black lines is the actual shape and the red ones is the change in the shape. Now we will see the analysis results of stresses. So for the zero iteration it is coming as 255 and for the optimized shape change result it is coming as 180. One more thing I want to highlight here is that you can see if you have not provided the shape card, you will not get the results in the change shape. So I'll show it again. What I'll do, I'll add a shape card here. Type all, options all, save, and run the analysis. Just I have added a shape card. So this results I am getting in the actual model, but actually the shape is different. So my analysis is completed. I haven't done anything, so analysis will definitely get completed. Now I will see the results. Apply. So this is the stress in original shape. If I change the iteration value, so this is the stress values in the changed shape. So it's up to you whether you want to see the shape changed results or the original shape results. You can also add here wireframe with the user. So this is the shape change result. So in this way, I have ended with this tutorial. So these are the options available in Hypermesh for the shape optimization. So I will close this. Click new. Also I will close this. So in this way, I have ended with the online training session day 9, shape optimization part 1. Thank you very much for attending this session. To improve the online training session, please help us by sharing your valuable comments at edu-support@india.altia.com. Also, if you find something interesting in this training series, then also please send your valuable comments at edu-support@india.altia.com. Your encouragement will help us to generate more such type of training sessions and videos. Thank you very much.